All right, we are good to go.
I'm just wondering whether there's a full screen. Yeah, here. Okay, now I have the full screen. All right, perfect. Okay, all right. Welcome everyone. Today I have the honor to introduce Joshuah Krissansen-Totton to you. He is. I invited him specifically to speak to us today. I've never had much of a chance to talk at conferences and things like this. But I read some of his papers and they're very interesting. And so that's the reason why I really wanted you to be here. Well, he was recently hired as an assistant professor at the University of Washington in the Department of Planetary of Earth and Space Sciences. And right now he's in the process of getting, I guess, his visa and his green card and everything approved. So he can't leave the United States right now. That's why we have him over Zoom. It's purely for kind of immigration reasons. So I suggested to him that at some point, maybe next year or so, you can come back and meet all of us in person. But I didn't want to kind of lose the chance of having you speak to us today already. Before he was, I guess you're still right now at UC Santa Cruz, right? Or have you already moved?
I'm actually back home in New Zealand at the moment, trying to get back into the US.
Okay, so okay, all right, that's even more complicated. So previously he was a Sagan Fellow at University of California, Santa Cruz, where he worked with Jonathan Fortney, that probably many of you know here in the group. He has written some interesting papers on astrobiology, on exoplanets, on TRAPPIST, so very related to what things that actually we just talked about 2 hours ago on one of our meetings. Yeah, he's originally from New Zealand. Then he did his PhD at University of Washington in Seattle. And well, then he did a Sagan Fellowship, and now he's back. Soon he's back in at the University of Washington. So today he's going to speak to us about his ongoing and recent work. So I let you maybe introduce your. Can you share your screen? Okay, so it's looking into the future and specifically anticipating. Sorry, I can't. Okay, now it works. Anticipating biosignatures, biosignature false positives in the 2020s. Yeah, we're very excited to have you here. I see you have some nice futuristic, basically pictures of the next generation of telescopes. One of them is already on, actually, many of them are in sky already. So I let you go ahead and welcome to Montreal, even if it's remotely. Thank you.
Thank you so much, Bjorn. So yes, I had really hoped to be there in person this week, but I am going to be back in the US for a little while. Unfortunately, the time zone difference from New Zealand is a bit difficult, so apologies in advance if I'm not the sharpest this morning, but hopefully I'll perk up as we go on. So this talk, I've given versions of this talk to different Earth and planetary science departments recently, and when I give the talk to those audiences, I usually spend the first few slides talking about these exciting new telescopes and how we very soon have this first opportunity to look for life beyond Earth. And this is true, of course, but since this is an astronomy audience, I probably don't need to convince you that big new telescopes are exciting. So instead, I thought I would begin with this statement, that despite these exciting telescopes, I think genuine exoplanet biosignatures will probably not be detected in the 2020s. And while this probably isn't particularly controversial, I think it's worth pausing to consider why this is true. So here is an exhaustive list of all the potentially characterizable, potentially habitable terrestrial exoplanets that we might hope to detect life on in the next 10 years. That's kind of it. And, we can argue, I've done different shades of gray because we could argue about which of these is really potentially habitable or really going to be amenable to atmospheric characterization. But, it's not going to be 20, right? It's going to be 3 or 5 or 7, a small handful of planets that are accessible in the next few years. And so even if you are very optimistic about life's emergence when conditions are right, this is going to be a small sample of planets to work with. And additionally, there's a lot of ways to kill a planet, right? Or to put that another way, there are many things that could impede planetary habitability. As versions of this diagram have kind of illustrate that, especially for these planets around late M dwarfs, there are a lot of ways we can imagine them to have lost their atmospheres and so on. And so the ability of planets to sustain long-lived, productive surface biospheres is potentially limited by many things. And so, all things considered, we'd have to be very lucky to find genuine signs of life in this small sample of planets. However, in addition to this list of potentially habitable, characterizable planets, there's also a list, perhaps a slightly longer list, of characterizable terrestrial exoplanets that are characterizable this decade. And so the observations of these objects, as well as the potentially habitable objects, will provide a really wonderful comparative planetology opportunity. So in the near future, we can look at the patterns in atmospheric composition, in particular, the presence or absence of potential biosignatures, right? So we can look at the atmospheres of these planets for potential biosignature gases, oxygen, ozone, methane, to try and understand, why do the potentially habitable planets not have or have these gases? Why do the uninhabitable planets have these gases if they're through non-biological processes? And, we really need these observations because planets are horrendously complicated. Important things are happening on all temporal and spatial scales. And so if we, have some observation of an atmospheric gas that could be produced by life, we have this grand challenge of ruling out all the planetary processes that could generate and maintain that gas in a planet's atmosphere. And so we have theory, right, to try and anticipate this, but it will be really helpful to have this sample of habitable and not habitable terrestrial planets kind of around what we think we know about non-biological planetary processes. And all of that, of course, is, in my mind at least, preparation for a purpose-built life detection mission or missions in subsequent decades where we might build a telescope capable of looking at a few dozen potentially habitable terrestrial exoplanets. And so the observations we'll make of terrestrial planets this decade will hopefully put us in a position to understand biosignature false positives more thoroughly going into these future missions. So with all that as kind of introduction, I wanted to summarize what I was going to discuss today. And mostly I want to convince you that testable and really tested theories of rocky planet evolution are needed to understand biosignature false positives and ultimately to detect life elsewhere. So this will be a two-part talk. I'll begin by saying a bit about oxygen as an example of this and how we can understand a non-biological oxygen buildup through models of whole planet evolution. I'll say a little bit about how Venus fits into this, and then make some tentative predictions for what we might observe in the next few years. And then time permitting, I'll say a bit about methane as well. Why is methane considered a good biosignature? How might we be fooled? What are ways you can make methane without life? And the, in my mind, fairly promising detectability prospects with JWST. So that's where we're heading. All right, so let's begin with oxygen then. I won't say too much about why oxygen is considered a good biosignature. I'm sure you've heard something about that before, but I just want to note that the argument is more sophisticated than just an analogy, and that there's all this oxygen in Earth's atmosphere produced by life, therefore we should look for oxygen elsewhere. It's really an evolutionary argument, and that there's a payoff for any carbon-based life that develops the capacity for oxygen-making photosynthesis. The substrates needed, CO2 and water, are virtually unlimited. And so this gives oxygenic photosynthesizers a selective advantage over other potential metabolisms. And so there's reason to expect this metabolism to dominate the biosphere elsewhere. It's also generally been thought to be difficult to maintain oxygen-rich atmospheres through purely lifeless geochemistry, through non-biological processes. And there's a growing literature on this, including review papers such as this one by Vicky Meadows that goes through and summarizes the various scenarios people have proposed for non-biological oxygen accumulation and the contextual observations you could make of those planets' atmospheres to kind of confirm or rule out that was what you're looking at. By and large, these scenarios are specific to low mass stars. And so when I got interested in this topic, I was curious about the general tendency of planets to oxygenate their atmospheres. And to explore this, you really do need a model of the whole planet and whole planet evolution. Something like 40% of Earth's mantle is oxygen by mass, and so you're needing to understand the whole oxygen budget of the planet. And so this is the model that myself and collaborators have been developing over the last few years that attempts to do this. And so we're primarily interested in oxygen buildup through hydrogen loss, right? So you can photodissociate water molecules, preferentially lose the hydrogen to space, leaving behind oxygen in the planet's atmosphere that can accumulate. Early on, this might partition into a magma ocean, but later on, when the planet cools off, you have these crustal sinks of oxygen, things like outgassing and reducing species, water rock reactions, a whole bunch of crustal processes that can draw down oxygen. And so we attempt to track this as the planet evolves in time. To do this self-consistently, you need to know the thermal state of the planet, you need to know the climate of the planets, because of these crustal processes are temperature dependent. So we've got an interior evolution and climate model in there. And then, of course, to know surface climate, you need to know where the volatiles are. So we're tracking CO2 and water fluxes as the planet evolves. As you can appreciate, there's many uncertainties in these processes. And so our approach is to just try and Monte-Carlo over all of that so that there are uncertain parameters representing initial conditions, atmospheric escape, carbon cycle, oxidation reactions, and so on. So everything you see as a model output will be the confidence interval. So just to give you a sense of what the model looks like, this is the model applied to the Earth through time. And crucially, this is a lifeless Earth, right? Because we're interested in the potential for non-biological oxygen buildup on rocky planets. And every subplot here is evolving in time, in years, and the x-axis here advancing logarithmically. And so I'll just explain some of what is going on here. This is the evolution of the thermal evolution of the mantle and surface temperature. You see the surface temperature dropping as the magma ocean phase ends here after a few million years. You can see that more clearly in this figure. This is the solidification of the magma ocean as it moves from the core mantle boundary to the surface of the planet. And then atmospheric composition, CO2, water, and oxygen is co-evolving with that interior evolution. Much of what is happening here can be explained by the energy budget of the planet. So it starts off hot, takes time to cool off, and when the thermal outgoing radiation drops below the runaway greenhouse limit here, the dashed line at a few million years, that is the time when the magma ocean ends, and that what was previously a steam-dominated atmosphere in blue here condenses out on the surface as liquid water. That's what this figure on the left is showing the liquid water depth, average of the whole planet. It's a few kilometers typically, and we're keeping track of, after that happens, the production of new crust. And crucially, all of this is with the end goal of tracking sources and sinks of oxygen through time, so we can anticipate atmospheric oxygenation. All right, so that's what the model looks like, or an example of what the model looks like. You might be wondering at this point, well, this is a complicated model. There's a lot going on here. Why should we trust all these parameterizations? And I don't want to oversell this, right? This isn't the finished theory of planets. This is, I imagine this model is kind of a collection of stories that we tell ourselves about how planets work based on our understanding of Earth and the solar system. And it just provides a way of tying together those stories and using them to make self-consistent, testable predictions for planets elsewhere. And it is at least reassuring, though, that when you tie together all these different pieces of planetary evolution, you do seem to get a self-consistent story that makes sense. And so the model does recover, the true modern Earth values for things like the thermal state and fluxes of carbon and crustal production and so on. And of course, some of that is by design, but it is reassuring that it works. And you can also try and validate individual components of the model. So this is our outgassing model here developed by Nick Wogan, a UW student working with me on this. And it seems to match pretty well with data from actual volcanoes. So and I should say that the atmospheric oxygen evolution part of the model is very much based off of other work that I've done, which I don't have time to discuss today, but work on the oxygenation of Earth's atmosphere and the sources and sinks of oxygen in Earth's atmosphere through time. So this is very much grounded in what we think we know about Earth's geochemical evolution. All right, so that's the model applied to a lifeless Earth. And the most important result for our purposes is here. After 4.5 billion years, the model predicts that there should be virtually no oxygen in the Earth's atmosphere. Oxygen here is in green. And so that's good news, right? For oxygen's biosignature. It tells you that in the absence of life, you would not expect a literal Earth twin to have a very oxygen-rich atmosphere. What we found, though, is that when you start to mess with the initial conditions of these planets, an otherwise Earth-like planet around a sun-like star can build up a lot of oxygen in its atmosphere. And I'll just briefly mention one of these scenarios that we identified, the water world scenario. So this is the exact same figure we had before, but now we've endowed our planet with tens to hundreds of Earth oceans worth of water. And so what happens when the magma ocean phase ends is that you're left with perhaps a few hundred kilometers of liquid water at the surface. This exerts an immense pressure on the crust below, which increases the solidus, the melting point of the crustal rocks. And this has the consequence of very rapidly shutting down the production of new crust, new melt, as has been described previously. But this has consequences for oxygen, because all your oxygen sinks depend on this, the production of new crust. And so the sinks go away, all you need is a very slight source of oxygen, a very slight leakage of hydrogen to space to be enough on long time scales to build up pretty substantial oxygen-rich atmospheres, as shown in green here. The oxygen starts to pick up after a few billion years due to the sink suppression. And you can see that on this figure as well, which is, every dot is a model run here. We're plotting final oxygen versus how much water you start with. And you can see that this isn't a problem for a few Earth oceans, but for tens to hundreds of Earth oceans, oxygen-rich atmospheres are a fairly likely outcome. And in the paper on this, we talk about how you might distinguish this non-biological oxygen on these water worlds from genuine biological oxygen. And Nick Cowan has a nice paper relevant to this on the sort of maximum height of mountains on planets. And so if you could detect continents, that would immediately rule out this kind of false positive, because it would tell you that the ocean depth was only so deep, and so that would tell you just had a few Earth oceans. More broadly, though, this kind of model can be used to simulate populations of planets and investigate the likelihood of non-biological oxygen buildup as a function of all sorts of astrophysical parameters. So this movie I'll start in a moment here, put together by Max Galloway, a former Santa Cruz undergraduate working with me. And so what this movie will show is a whole bunch of planets from 0.7 to 1.3 AU around the sun. And we're tracking the evolution of atmospheric oxygen, carbon dioxide, and water vapor, as well as surface temperature, which is the color bar here. And you'll see after a few million years, the magma ocean ends, you start to see interesting trends in atmospheric composition as a function of orbital separation. The dashed vertical line here is the inner edge of the habitable zone creeping outwards as the sun is getting brighter. And you do see a population of planets in the habitable zone that have oxygen-rich atmospheres and are lifeless, which obviously require some investigation. Now, what is particularly interesting is if you pause that movie at 4.5 billion years and you focus on Venus-like orbital separations, 0.7 AU, you see an interesting population of planets. You see some planets, as highlighted in the yellow circles here, that look a lot like Venus, 100 bar CO2 and virtually no water vapor or oxygen in their atmospheres. But you also see planets that, with the same orbital separation, that look nothing like Venus, that have a whole lot of oxygen in their atmospheres and or steam. And so in my mind, it's, if we want to use oxygen as a biosignature, it's really crucial to understand why Venus does not have an oxygen-rich atmosphere due to hydrogen loss, despite this seemingly perfectly plausible outcome where it could have had a very oxygen-rich atmosphere. So I should also briefly mention there are, of course, other intrinsically interesting questions about Venus. Was it habitable in the past? There are differing views on this in the planetary science literature. People have applied 3D climate models to show, yes, you could have a temperate early Venus. This has recently been challenged by other models showing that while this temperate state is stable, you might have trouble transitioning to it from an early steam atmosphere, just due to the feedbacks that keep the planet hot. On the geology side, we know there are regions of the crust on Venus, the tesseract ring, that are very old, very tectonically deformed, within which there is some evidence of felsic crust, and even people have proposed evidence for geomorphological evidence for past liquid water activity. This is, of course, controversial. Generally speaking, recent habitability has been hard to reconcile with the lack of oxygen in Venus's atmosphere. Because if you want to have had Venus habitable recently, you have to explain, when that hydrogen went away, how you got rid of that oxygen in such a short time. And so with all of this in mind, I thought it would be interesting to apply our evolutionary model to Venus to try and shed some light on the fate of oxygen and the possibility of past habitability. And to cut a long story short, this is what you get when you apply that same model as before to Venus's evolution. So I'm getting a bit of an echo. Is the sound okay for all of you?
Yes, it sounds great for us.
Okay, great. So the outputs on the left are showing, well, I should say there are essentially two ways to successfully recover modern Venus. The model outputs on the left, where Venus never experienced a habitable time. You transition directly from this early magma ocean to the modern runaway greenhouse state. You never have liquid water. The water is in the atmosphere is gradually lost to space. Oxygen is mopped up by sinks, and this is consistent with a lot of traces in the atmosphere, argon and helium. So that's self-consistent. There's also a whole different set of model outputs where you get to the same endpoint, you get to the same modern Venus with its high surface temperature, but you experience an epoch of transient habitability where you have perhaps 100 meters of global oceans. And before, as the sun is getting brighter, you go back into runaway greenhouse, losing that remaining water to space, mopping up the oxygen through crustal sinks and returning to a CO2-rich atmosphere. And by and large, the model doesn't really prefer one solution over another. They are, well, you can make arguments for why one is more plausible than the other, but both seem to be consistent with everything we think we know about Venus, the bulk atmospheric composition, various trace gas, traces of outgassing through time, estimates of heat flow, and so on. So understanding, in my view, this was kind of a frustrating result, but it really emphasizes the need to go back to Venus, to make some in situ measurements, to understand its evolution. Unfortunately, we are getting now 3 missions to Venus in the near future, Da Vinci, Veritas, and the European Envision mission, which will do exactly this, measuring the descent probe will measure trace gases and isotopes to really pin down the escape history of Venus and the possible fate of oxygen, as well as orbiters that will constrain the sort of internal state of Venus, as well as do near-infrared imaging of the surface, which might give us a better sense of the surface rock composition and redox conditions, all of which are going to inform our understanding of Venus evolution. But of course, sooner than that, we're going to get constraints on sort of Venus analogs elsewhere, on terrestrial exoplanets, both Venus analogs and more temperate terrestrial exoplanets. And so next I wanted to say a little bit about the TRAPPIST system and application of the model to some of these exoplanets. Now, of course, these terrestrial planets are potentially quite different to their solar system analogs in that they have been subjected to the extended pre-main sequence of their low mass host stars, so potentially hundreds of millions of years of very high XUV and volumetric fluxes, potential for a lot of atmospheric loss. But we're not going in totally blind. There are pretty good mass constraints on this system through TQVs in particular for these, and these mass constraints allow the surface water inventory to be constrained, especially for these inner planets where any water must be present as steam, which we'd expect to inflate the radius of the planet. So that lack of radius inflation puts a pretty stringent upper limit on the current surface water content of these planets. And so we applied our evolutionary model to the TRAPPIST system to both try and recover these water constraints as well as fold in the stellar evolution of the very low mass star. And so again, cutting a long story short, this is the same model as before applied to, in this case, TRAPPIST-1e, and I'm not going to go through everything here. It's essentially the same model as before. So we've got, again, the energy budget is dictating a lot of this, but now it takes hundreds of millions of years for the outgoing long-wave radiation to drop below the runaway greenhouse limit due to that extended pre-main sequence. So you have a magma ocean lasting perhaps a few hundred million years in a very long time to have a steam atmosphere and be losing hydrogen, potentially generating oxygen. And this is just the thermal evolution of the mantle and the surface, the water. But that extended pre-main sequence means there's greater potential for oxygen build up, although once that is over, you still have crustal sinks to mop up the oxygen. And so we sort of attempted to fold that all together to make some predictions. And here are what you might generously call probability distributions for the current atmospheric composition of the TRAPPIST planets based on those sorts of evolutionary model calculations. And I put probability distributions in quotation marks because there is, of course, a degree of arbitrariness in what you choose for kind of initial volatile content. But I think nonetheless, it's interesting to look at these distributions for kind of the qualitative trends. You see all sorts of interesting things going on here, bimodal distribution and atmospheric CO2. So this is like partial pressure, surface partial pressure in bar on the x-axis here for the planets B through G in the TRAPPIST system. You have some planets that lose all their atmospheres, unsurprisingly, but you also have many model runs where atmospheres are retained. And probably the main thing that you notice here is that atmospheric oxygen, as shown in cyan, the chances of very oxygen-rich atmospheres diminish as you move outwards in the system. And that can be seen more clearly in this figure, where this is the percentage of model runs with very oxygen-rich atmospheres for B through G. The different symbols and colors just represent different scenarios, different metallic core sizes or initial volatile inventories and so on. But the trend is basically the same in that for these inner planets, very oxygen-rich atmospheres would be unsurprising due to their large potential for hydrogen loss, whereas as you move outwards, the oxygen sinks tend to win, and it's less likely that oxygen will be retained for 8 billion years, or the age of the system. The one possible exception to that is that if you insist that the low densities of the outer planets are attributable to surface volatile inventories, ice, then you get that pressure, the pressure effect that I described earlier for the water world. The immense pressure of the surface water suppresses melt production, suppresses oxygen sinks, and you're more likely to be left with an oxygen-rich atmosphere. And just to, I'm sure you're all aware of this, but this is something that is imminently testable with JWST. These are some simulations done by Jake Lustergager looking at detectability of oxygen, CO2, and water features in this case, TRAPPIST-1b's atmosphere, and assuming you can get a handle on the stellar noise, this should be doable. It may also be possible to do this from the ground in the near future as well. And in fact, here's a fun list of all the papers I found doing sort of simulated TRAPPIST observations, showing that you should be able to characterize the atmosphere if all goes to plan. And while, of course, the TRAPPIST system is unique, there are other targets for which you might be able to do this. This is the recently discovered Speculos 2 system, LP899, which has a one sort of Venus analog, one habitable planet, and you can make similar predictions for oxygen accumulation in this system to do the comparative planetology more broadly. All right, well, what's potentially more useful here than just, here's my prediction, is it right or wrong, is that you can use these models to understand mechanism and to really get to the bottom of what planetary processes, what uncertain variables are really driving atmospheric outcomes. And so this is what this weird looking figure is showing. On the y-axis here, we've got all the unknowns, all the unknown parameters in the model, initial composition, atmospheric escape, carbon cycle, interior exchange, how clouds work. And then this is for the TRAPPIST system here, we've got the planets on the x-axis. And each dot is just a simple linear correlation between that unknown parameter and how much oxygen you're left with after 8 billion years. And so here's an example of that for initial water versus oxygen. So the size of that dot is the R-squared value, and the color is the R-squared value, and the size is related to the significance of that correlation. And so what this enables you to do is just glance at the figure and immediately say something about what is controlling atmospheric oxygenation on these planets. And you see that for the inner planets B and C, it's somewhat simple, and that all that matters is how much water you start with, what's the internal heating, and how do the surface sinks work. Whereas for these outer planets, oxygenation is controlled by a lot of other stuff. The details of atmospheric escape physics seem to matter for these outer planets. Cloud feedback seem to matter. So understanding oxygen or lack thereof in these planets is going to be a bit more nuanced. All right, so that's everything I wanted to say about oxygen. But in the time remaining, I did want to mention something about methane as a biosignature and its false positives. And the motivation for this is fairly clear. This is a figure showing Earth's atmospheric evolution through time. Oxygen has probably only had really readily detectable abundances for a relatively small portion of Earth's history. And so if we want to ultimately do life detection on a large sample of planets, we don't necessarily want to put all our eggs in one basket. And one thing we do know from trying to understand Earth evolution is that there seems to have been, or at least there's evidence for high methane abundances on the early Earth before there was any oxygen around, and that methane was likely overwhelmingly produced by life. And so it's reasonable to wonder, well, could the presence of methane in oxygen-free atmospheres, terrestrial planet atmospheres, be a biosignature? And so this is the argument for that in a nutshell, and I'll go through these three parts. In turn, that essentially, if life is common in the universe, we might expect methane-producing biospheres to be common. There are ways to make methane without life, but I will argue that, at least for the most obvious scenarios, there are contextual observations we could make to identify those false positives. And this is worth thinking about because methane, biogenic methane is imminently detectable, I think, with instruments this decade. All right, so why methane is a biosignature? Life on Earth makes methane through a number of reactions, net metabolic reactions, and crucially, all of these are they use substrates that we'd expect to be common on rocky planets: hydrogen, CO outgassing products, CO2 and water present on habitable planets by definition. And so this is methanogenesis is kind of an obvious strategy that you might expect to evolve in response to sources of readily available environmental free energy. Additionally, though, you get a boost of methane from the decay of organic matter, which will occur for any carbon-based life. So there's reason to think that methane production would evolve and be quite substantial. And indeed, when we look at Earth's history, it seems to be the case that methane-producing microbes emerge very early on, essentially at the same time as the origin of life within era. And when people construct models of microbial ecosystems, making different assumptions about what metabolisms are present, it is often found that very methane-rich atmospheres are an outcome of these biospheres. So that's kind of a brief introduction to methane as a biosignature, but what we have been thinking about, what are the ways you might be fooled? How might you make very methane-rich atmospheres on lifeless but potentially habitable terrestrial exoplanets? And this is not new. People have been speculating about this for decades. For the most part, though, papers often mention methane as a possible sign of life, but follow it up with caveats along the lines of, well, there are always other processes that make methane, though, so is it really that useful? And so what we wanted to do was to try and quantify some of these most obvious mechanisms for non-biological methane production to really figure out how much of a problem are these potential false positives. And the important point to start with is that in terrestrial planet atmospheres, obviously the story is different for giant planets and sub-Neptune. So for genuine terrestrial planets, the lifetime of methane in the atmosphere is short, regardless of atmospheric composition. This is true for oxidizing atmospheres as well as for reducing atmospheres. I'm not going to go over the photochemistry here, but it is something you can very, very readily verify, as Maggie has done, a Santa Cruz student working with me on this, with an off-the-shelf photochemical model showing you need substantial fluxes of methane to maintain detectable abundances of methane in rocky planet atmospheres. And this is consistent with a lot of previous photochemical models. So the question really becomes, could you sustain large fluxes of methane on lifeless planets? Right? And a good starting point for this discussion is the current budget of methane fluxes in and out of Earth's atmosphere. This is, of course, of interest to anthropogenic climate change. And this figure is from the latest IPCC report, where you see all the anthropogenic sources of methane as well as the biological sources of methane. Now, you do see here a small but not insignificant geological source of methane. But what is important here is that the term geological source doesn't really mean non-biological as we understand it. This is what is termed geological is really a lot of processing of formerly living biomass, organic matter in the crust being heated and decomposed to produce methane. The true non-biological source of methane in this geological component is vanishingly small. So small that no one really has a great handle on what it is. It's almost an impossible question to answer, right? Because the biosphere has so thoroughly modified the composition of Earth's crust through time that you have to ask a really difficult counterfactual, like what would the methane fluxes be if Earth had evolved in a totally lifeless state? So rather than try and do this, we took an alternative kind of first principles approach where we looked at the individual processes that might make methane and tried to estimate how they might scale up on other planets. And so Nick Wogan, a UW grad student, worked with me on this, developing a model of magmatic outgassing on rocky planets, and showed that when you calculate methane fluxes for a broad range of planetary compositions, temperature, pressure, composition of the melt, oxygen, fugacity, you invariably find it's hard to make a lot of methane. Methane fluxes are typically low. And in the rare instances where you do make a lot of methane, it tends to also be accompanied by a lot of carbon monoxide, even higher fluxes of carbon monoxide from volcanoes. And the reason for this is, and we wouldn't expect this in the case of an inhabited planet. The reason for this is that CO2 and methane are sort of at opposite ends of the redox spectrum, separated by 8 electrons. And so if you want to have an equilibrium process that makes a lot of methane, you tend, if you want to shift things in that direction, you tend to also produce a lot of carbon monoxide. It's hard to produce both extremes without producing the intermediate carbon monoxide. This is different to what you'd expect for an inhabited planet, where CO is free food for microbes, essentially. This is a very easy metabolism to do. And so we wouldn't expect CO to build up on inhabited planets. And this is something that that has been reported in previous models. So this figure is arguing that the atmospheric ratio of CO to methane might be potentially diagnostic in distinguishing these habitable or methane produced from life versus non-biological equilibrium processes such as outgassing. And so we're plotting here that ratio for a bunch of model biospheres is shown by these colors on the bottom, and then the blue is lifeless planets. And so you can see that life tends to draw down carbon dioxide, where you get high CO to methane ratios on these lifeless planets. And obviously the details here are going to be cell dependent, but I think this is a promising start. Similar arguments apply for methane produced by impacts. Most commonly talked about false positive for methane biosignatures is sort of low temperature systems, water rock reactions, producing hydrogen gas that can then react with CO2 to make methane. In previous work, I sort of tried to crudely quantify this based on, so this equation here is just like a Drake equation, like multiplicative factors to estimate the maximum methane flux you might get from this, this sequence of reactions for an arbitrary terrestrial planet. And so that you get this probability distribution here, even making very generous assumptions, the methane fluxes are much less than the current biological flux. And Maggie has since followed up on this. The pink distribution here is exactly the same as the blue distribution here. It's just now in log space. And here are various estimates from the literature of non-biological methane fluxes, particularly from water rock reactions such as those described. And they're generally consistent with this kind of upper limit from the distribution, and all are much less than the current biological flux. In the interest of time, I think I'll skip over sort of Titan as an example of non-biological methane, but happy to chat about that if you're curious. But where we kind of came to in the end with this was that, yes, there are these various scenarios for how you can make methane-rich atmospheres without life, but we think there are contextual observations you could make, the other atmospheric constituents, that would alert you to the fact that this is the potential source of methane that we were looking at. And just to convince you this is worth thinking about, methane is among the most detectable molecules in terrestrial planet atmospheres. This is a simulated retrieval I did with, this is for using near-spec prism, looking at an Earth-like, Archean Earth-like TRAPPIST-1e, 10 transits, seem to be enough to get the methane and CO2. And there's been other simulated observations that essentially show the same result. You should be able to get methane for these planets. In fact, there have already been claims of methane detections using Hubble on terrestrial planet atmospheres. This is Hubble observations of GJ1132b, which is not a habitable planet. Now these observations have been, well, this processing of data has been challenged and this detection has been challenged. But the fact that it's almost possible, or at the limits of what is possible with Hubble, makes me think this should be doable with JWST, although I'd be very curious to get your, this audience's perspective on that. And this is the corner plot from my retrieval showing that you should not only be able to get a detection, but also a crude abundance constraint on the methane, the CO2, and maybe an upper limit on the CO, everything you need in principle to identify or rule out some of these non-biological methane production scenarios. And in fact, biological quantities of methane are going to be much easier to detect with JWST than biological quantities of oxygen or ozone, which are probably not going to be doable in so nominal mission lifetime. All right, I will skip over that, and this is just a summary of that argument for methane. I do want to add the caveat, though, that there's a lot we don't know here. The parameter space for ways you can make methane and planetary crusts is vast, and this laundry list here is kind of more for a planetary science audience, but there's a lot of unknowns here in the potential of our planets to generate methane. And so any methane detection in the next few years should obviously be treated with a lot of caution. Unlike for oxygen, where we do have these models for sort of whole planet evolution, there's no such model for non-biological methane accumulation through time. All right, so just to wrap up then, this is a schematic of what the next few years might look like. In addition to continuing to learn more about Venus and Earth evolution, we are suddenly going to have atmospheric constraints on a handful of terrestrial exoplanets, both uninhabitable and potentially habitable. And so these constraints can be compared to evolutionary models, such as the one that I've talked about, but we'll obviously need an ensemble of models to make sense of all this, to try to understand things like non-biological oxygen accumulation or lack thereof. And so hopefully if we do all this down the line, we'll be in a better place to interpret genuine biosignatures with some future life-finding mission. We'll have the grounded contextual observation of planetary atmospheres so that we can properly interpret oxygen and methane detections. So with that, I want to leave some time for questions, so I'll just leave up my conclusions. There are some papers on this stuff if you want to know more. Yeah, very happy to get your questions and comments. Thanks so much.
Thank you, Joshua. That was great. Can you see the audience actually? Yeah, you can see some of the audience, right?
Yeah.
Okay. I hope that helped a bit. I put the microphone on mute so that you wouldn't hear this echo anymore. Did that help a bit?
Yeah, that was fine.
Okay, all right. Okay, so we have at least 5 minutes for questions. If people, Lloyd?
Yes, hi. So if it's difficult to produce methane, how come is Titan rich in methane? Can you explain why?
Yeah, let me go back to the Titan slides here. Right. Okay, so Titan, of course, has the lifetime of methane in Titan's atmosphere is short. And so this has always been kind of a puzzle. What is the replenishing source of Titan, of methane on Titan? But what is kind of most relevant for the habitable exoplanet context is that if you were to take something with a Titan-like composition and move it into the habitable zone and melt all the ice and release any methane in those volatile reservoirs, then additionally expose that atmosphere to kind of the higher UV fluxes of the inner solar system, you find that the lifetime of methane in the atmosphere will be quite short. And so that's what Maggie did here, essentially taking Titan, scaling up to be Earth size, and then calculating how long, once you melt everything, how long does that methane hang around for? And so we're essentially plotting here the water mass fraction of the planet, and how long that methane would hang around for 4 different sort of carbon inventories. And unless your water mass fraction is getting up to a sizable chunk of the whole planet, the methane just isn't going to hang around. It's going to be photo-associated, and the hydrogen is going to be lost very rapidly. So it's quite challenging to replenish the methane once you start to heat up the planet. And for the planets that do have these really high water mass fractions, you would expect to know that from density constraints. And so you would get some clue that there was a very large volatile reservoir potentially replenishing your methane. Now, the story does get a little more complicated when you start to worry about clathorates as a potential reservoir to replenish the methane. But methane clathorates are less dense than liquid water. And so there becomes a kind of a climate stability issue, and that if it heats up a little bit, you destabilize the clathorates, you melt them, releasing the methane. And so no one's sort of explicitly done that modeling yet, but I suspect that, again, in the habitable zone, you're just going to very rapidly put all the methane in the atmosphere where it will be destroyed. So that's the Titan analog story in a nutshell.
So I have one short follow-up question to this. In this plot that you showed from the Thompson, I haven't had the chance to read this paper yet. Are you considering that any kind of cloud coverage or haze coverage could actually lower your methane destruction rate?
So in that particular calculation, we're just doing diffusion limited escape, which is probably a conservative estimate of methane destruction, because in terrestrial planet atmospheres, there'll be OH radicals around. I wouldn't expect cloud formation to slow the methane loss. I mean, the main thing you have to worry about is anything that cools the upper atmosphere and sort of throttles the hydrogen loss. But it's hard to imagine that slowing it by the orders of magnitude you would need to limit the methane lifetime for these temperate planets.
Okay, maybe another question. Maybe I have one last question if we have time. You showed basically in this water world scenario where you showed that that basically the oxygen can build up. You had like one of your evolution models for the water world, and somehow, I think like roughly 1 billion years or so, all of a sudden the oxygen abundance shot up a lot. But I'm not sure. Can you go back to that slide potentially?
This is probably the one you're thinking of.
Yeah, exactly. So can you give like a more conceptual understanding of why it stays down at like 100 million years and then at 1 billion years, so all of a sudden it rises again?
It's essentially just when the source sink balance flips. And so during this time, the first few 100 million years, so this early evolution is just equilibrium with the magma ocean, right? So this isn't really a source sink process. This is just equilibrium oxygen. We've got the mantle as a melt. But then subsequently here, this is after the magma ocean is frozen. Early on in this planet's evolution, the mantle is still quite hot. You're still producing a lot of new crusts. There's a lot of potential volatiles to react with oxygen coming out of the interior, a lot of fresh crust that oxygen can react with. And so these sinks hold oxygen essentially zero abundance. I mean, there's a numerical cutoff here. My model isn't capable of doing lower oxygen abundances, but it's essentially zero oxygen for most model runs during this time. But then as the mantle cools off, as the planet ages, those sinks diminish, and they diminish rapidly because the huge pressure of the crust, the huge pressure of the ocean on the crust is making it harder to melt rock. And so after a few 100 million years, 1 billion years, that crustal production tends to shut off. That's this red plot here is that showing that shutdown in crustal production. So that's the sinks shut off, and then you can begin to rapidly accumulate oxygen subsequently. So hopefully that can answer your question.
Okay, I guess the time scale is not so well constrained. I guess from a posterior there, it looks a bit like that could happen after 600 million years, or it could happen after 2 billion years.
Sure. It depends a lot on initial abundances and the details of escape, which is kind of why there's so much scatter in this next figure. But it's qualitatively true that as you increase the amount of starting water, this becomes more and more likely.
Okay. Yeah, very interesting. If there are no more questions, we will pass the hour anyway. Then let's give Joshua one more round of applause, and thank you so much.
Thank you all.
And we will stay in touch. I will send you an email probably today or so that we can talk more.
Sounds great.
Thank you so much.
Bye.
Bye. I'm going to turn off the recording now.